Okay, in this presentation we're going to evaluate this integral here. Now the integral is from 0 to 1, and it's the integral of x to the power of 10 times 1 minus x to the power of 9 dx. Now in the first instance it doesn't look like it has anything directly connected to statistics or probability distributions, but it is in fact can be characterized using the beta function. So you can sort of see the shape there, x to the power of alpha minus 1 times 1 minus x to the power of lambda minus 1, where the beta function is parameterized by the inputs alpha and lambda. By the way, I'm just sort of picking those as sort of general sort of notation there. It doesn't really mean anything. Now these are the beta function of alpha and lambda can be written as the multiple, the product of the gamma function of alpha times the gamma function of lambda divided by the gamma function of alpha plus lambda. Okay, and so it helps to know what the gamma functions are all about. They're actually, from the point of view of looking at them from the point of view of factorials, fairly straightforward. The gamma function of n is simply n minus 1 factorial. So the gamma function of 4, let's say, is 3 factorial, which is 6. The gamma function of 5 would be 4 factorial, which is 24, and so on. Okay, all of the sort of tricks that we might use for the factorials also come into play there. So for example, the gamma function of n plus 1 is n factorial, and we can write that as n times the gamma function of n. So you can disregard those things there. It's just a typesetting error. Likewise, the gamma function of n can be written as n minus 1 factorial, which is n minus 1 times the gamma function of n minus 1. So all those little tricks help out a lot. Okay, so yeah, the gamma function, handy to know, and also the gamma function. The beta function and the gamma function, both handy to know. Okay, so this is the question here. The beta function is as follows: x to the power of 10 times 1 minus x to the power of 9. So if we're parameterizing it, we can express 10 as 11 minus 1, and that means that alpha is 11, and then 1 minus x to the power of 9, lambda minus 1, lambda is equal to 10. Okay, so those are the two inputs. Oh, sorry, P and Q here. So P and Q. So we'll just work with P and Q there. Okay, so it has that general form there. Okay, and we can identify P and Q as 11 and 10 respectively. So what we could do now is express it out as the gamma function of P, which is P minus 1 factorial, times the gamma function of Q, which is Q minus 1 factorial, divided by the gamma function of P plus Q minus 1 factorial. Okay, so these are causing me hassle there, so I'll just do this by pen and paper. So what we end up with is, I'll just go down here. The answer works out to be a very tiny number here, so that's not really the point. It works out to be 10 factorial times 9 factorial over 20 factorial. Okay, now this is a bit of number crunching. What we could do is express that as 9 factorial over the 10 factorial times 20 times 19 times 18 all the way down to 10 factorial. Now the 10 factorials will cancel out, and so what you could do there is just a little bit of number crunching, just try and sort of cancel out pairs of numbers, and essentially what you should get is cancel out the values in the numerator with the corresponding values in the denominator, and you should end up with this value here, 0.0000051443. Okay, you can check that with your calculator. So a bit of a tricky, cumbersome answer to deal with, but overall it's very straightforward, really. You know, usually you might get these, if you do face these, you won't get anything like 10 and 9, you probably get something like 3 and 4 and be easier to work out. Alright, we'll leave it there.